You're using one right now, a computer. But could you actually explain how it works? I'm not talking about, you click stuff and stuff happens. I mean, what happens when you click what's going on inside that screen full of cat videos, crypto scams, and poorly formatted spreadsheets? Here's the thing, most of us have no idea how computers work. And the worst part, we think we do. RAM is memory. Not quite. The CPU is like a brain, sort of, but also no. Binary is just ones and zeros. True, but also what the hell does that even mean? In this video, I'm going to walk you through how computers really work. But in plain English, no buzzwords, no boring graphs, just ridiculous metaphors, dumb jokes, and way too many AI-generated images. Buckle up. This is everything you think you know about computers. Destroyed.
A computer is not magic, although it might feel that way when it fixes itself just because you restarted it. Most people think a computer is just that thing I use to check emails and watch YouTube. But there's way more going on under the hood. So let's strip it down to the basics. No jargon, no buzzwords, no complicated diagrams. A computer is, at its core, a machine that follows instructions. That's it. That's the whole definition. You give it input, it processes that input using logic and electricity, and then it gives you output. The input can be anything from a key press to a mouse click, to you yelling, "Why are you not working?" at the screen. The processing is done by internal parts, tiny little electronic workers, following very specific instructions, written by even more tired humans. And the output. That's what you see on your screen, hear through your speakers, or curse at when something crashes. If a computer were a restaurant, input is your order, processing is the kitchen, and output is the sad burger that looks nothing like the ad. But computers aren't smart. They don't know what you want. They only know exactly what you tell them, nothing more. If you tell your computer to open a file, it won't think, "Oh, I know what they mean." It'll say, "Which file? Where is it? What program do I use? Be specific, or I panic." That's why programming is hard, because computers are dumb, just very fast at being dumb. They follow rules. That's all they do. They can follow billions of rules per second, but they never improvise. If you give a computer a slightly wrong command, it won't try to help you, it'll just stop working and maybe flash a blue screen to ruin your day. This is also why they're powerful, because they're not creative, they're consistent. They'll do exactly what they're told every time, for better or worse. Every computer, no matter how fancy, boils down to the same three-part process: input, process, output. Input is how you communicate with the computer keyboard, mouse, microphone, camera, touchscreen, whatever. Processing is where the magic happens, inside chips and circuits you can't even see. Output is what comes back to you: a video, a notification, a file, or a fan that sounds like it's about to take off. The core components of any computer are hardware and software. Hardware is the physical stuff, the keyboard, the screen, the motherboard, the mouse, and yes, the part that stabs your foot when you drop it. Software is the set of instructions that tells the hardware what to do. Without software, the hardware just sits there looking pretty and doing nothing. Without hardware, the software is like a ghost floating around with no body to control. Together, hardware and software form the ultimate power couple. One gives the orders, the other carries them out. This relationship is what makes your computer tick and occasionally makes it explode metaphorically when something crashes. Every time you press a key, click a button, or scroll through memes, you're triggering a chain reaction inside your computer. It receives your input, processes it using a set of instructions, and outputs something for you to interact with. And this all happens so fast you usually don't even notice, unless it lags, and then you definitely notice. But just because it feels like magic doesn't mean it is. It's just extremely fast logic. Logic powered by electricity, tiny circuits, and a shocking amount of trial and error from the people who built it. Think of your computer like a well-trained dog. It can do tricks, but only the ones it was taught. If you ask it to do something it doesn't understand, it'll either ignore you or start spinning in circles until you force a restart. So no, your computer isn't thinking, guessing, or feeling. It's just following rules, one by one, incredibly quickly, and often without any context. And the better the instructions, the better it performs. That's why we write software to turn human wants into computer commands. If you ever feel like your computer is outsmarting you, don't worry. It's not smarter than you. It's just better at doing exactly what it's told. And now that you understand what a computer really is, we can start diving into its parts. Because behind that shiny screen is a whole universe of tiny jobs being done at lightning speed. Next up, the CPU. Everyone calls it the brain, but it's more like a manager with ADHD. Let's talk about the CPU. It stands for Central Processing Unit, but nobody ever calls it that unless they're trying to sound smart in front of a date. Most people just call it the brain of the computer, and honestly, it's kind of an insult to actual brains. The CPU isn't smart. It doesn't make decisions, doesn't know anything, just follows instructions really fast and in the exact order you give it. Think of the CPU like a hyperactive assistant with no critical thinking skills. You tell it, do this, then do that, and it goes okay. It sprints full speed into the task. Even if the task makes no sense. Even if it's dangerous. Even if it's just open and close calculator 1,000 times, it will still do it enthusiastically, over and over again. The CPU doesn't care about logic or consequences. It just wants jobs to do. In fact, the only reason your computer doesn't melt itself daily is because of the other parts telling the CPU to slow down or cool off. The CPU does the bulk of the number crunching and logic processing inside your machine. It runs the code, processes your clicks, decides when to open that tab full of cursed fan fiction you left running in the background. When you open a program, the CPU springs into action, fetches the code from your storage, loads it into RAM, and then starts executing instructions one by one. It's like flipping through a recipe book really fast and cooking everything at once. Except the CPU doesn't know what it's cooking. It's just following steps. Step 1. Add water. Step 2. Set oven to 4 billion degrees. Step 3. Panic. That's basically how it works. Inside the CPU are billions of tiny switches called transistors. Each transistor can be on or off like a light switch. Combine a few billion of those, and you can make them do math, compare values, make decisions, and even play Fortnite badly. The faster the CPU, the more instructions it can run per second. That's what we call the clock speed, usually measured in gigahertz. 1 gigahertz means 1 billion cycles per second. So a 3.5 gigahertz CPU can theoretically handle 3.5 billion instructions every second, which sounds insane, and it is. But here's the thing. The CPU doesn't do everything. It just coordinates everything. It hands off graphics to the GPU, storage tasks to the SSD, and annoying notifications to whoever will take them. So while it gets all the credit, the CPU is more like a frantic manager in an office filled with interns. It yells out tasks, checks if they're done, and then starts yelling again. If the CPU stops working, the whole system collapses. But if it gets overloaded, things just slow down, or crash, or heat up until your laptop could cook eggs. That's why cooling the CPU is so important. Those little fans, they're not just there to make noise. Yeah, they're fighting to keep your CPU from becoming a tiny volcano. And modern CPUs get hot. Like, don't touch that metal hot. That's why gamers and tech nerds spend so much money on giant fans, liquid cooling systems, and RGB lights that don't actually help but look cool. Now here's the part people always get wrong. More gigahertz does not always mean faster performance. It depends on how efficient the CPU is, how many cores it has, and how well your software uses them. Wait, cores? Yes, CPUs can have multiple cores. That means they can do several tasks at once. Think of cores like extra workers in the brain factory. More cores equals more multitasking, but only if the software knows how to use them. If your program only uses one core, the rest just sit there bored, wondering when they'll get their turn. This is why some tasks feel slow even on powerful machines. It's not always the CPU's fault. Sometimes the software is just lazy. But overall, the CPU is the unsung hero of your device. It doesn't glow. It doesn't get flashy ads. But without it, you'd be staring at a very expensive piece of plastic and glass. So the next time your computer lags or crashes, don't get mad at the CPU. It's just a little guy doing 10 million things a second and wondering why you opened 42 tabs and tried to play a 4K video at the same time. Give it a break, or at least give it a better fan. Let's clear something up right now. RAM is not your computer's memory. Well, it is, but not the way you think. RAM stands for Random Access Memory. Sounds like a 90s punk band, but is actually one of the most misunderstood parts of a computer. People think RAM is where your files are stored, like documents or videos or that weird folder you forgot to delete. Nope. That's your storage or hard drive or SSD. RAM is more like your computer's short-term memory. It's what your computer uses to think while it's working on stuff. Imagine your computer as a chef. Storage is the pantry where all your ingredients are kept. RAM is the countertop. The more countertop space you have, the more ingredients you can lay out and work with at once. If your countertop is small, you can still cook, but you'll be constantly running back and forth to the pantry. That's what it's like using a computer with not enough RAM. It has to swap things back and forth from storage constantly, which slows everything down. RAM is fast. It's like ridiculously fast compared to your storage. But it's also temporary. When you turn off your computer, everything in RAM disappears instantly. It's like a whiteboard that gets wiped clean the moment you shut down. This is why your unsaved Word doc vanishes if your laptop dies. It was sitting in RAM, not storage. Your operating system, apps, browser tabs, and basically everything running live in RAM, at least temporarily. The more you multitask, the more RAM you use. Have 25 Chrome tabs open? That's RAM, running Photoshop, Discord, and a game at the same time. That's a RAM feast. When your RAM gets full, your computer starts to struggle. It tries to fake it by using something called a page file, which offloads stuff to the storage drive. But that's like using a snail instead of a race car. Yes, technically it works, but don't expect any records to be broken. That's why more RAM can make your computer feel faster, even if your CPU and storage stay the same. It just gives your system more breathing room. But again, more isn't always better. If you mostly check email and watch videos, 32 gigabytes of RAM is like giving a hamster a Ferrari, overkill for casual use. 8 to 16 gigs is more than enough. Unless you're editing video, running virtual machines, or building the next space rocket in Blender, you don't need to go crazy. RAM also comes in different speeds, and yes, faster RAM can help in certain scenarios. But unless you're a benchmark-obsessed nerd, you probably won't notice the difference. And don't stress over dual channel, quad channel, or whatever channel. They're all just ways of organizing RAM sticks to work together more efficiently. If you want to upgrade your RAM, just make sure you buy the right type and that your computer can handle it. Oh, and match the sticks if you can. Computers are picky. Mismatched RAM is like trying to run a relay race with two people wearing different shoes. This might work, but it won't be pretty. So, to recap, RAM is fast, temporary workspace, not long-term memory. It lets your computer juggle more things at once, but it forgets everything the moment the power goes out. It's not where your files live, it's where your processes live. And yes, Chrome will eat all of it if you let it, because Chrome is not your friend. If RAM is your computer's short-term memory, then storage is its long-term memory. This is where your files live. It's all your photos, videos, documents, apps, games, and downloads. They're all stored here. Even the terrible selfies you swore you deleted in 2014. Storage comes in two main types: hard drives and solid-state drives. Hard drives are the old-school kind with spinning magnetic disks inside. Yes, they actually spin, like tiny metal records. It's a little arm that moves across the disk to read or write data, kind of like a record player needle. This means they're mechanical, which also means they're slow, fragile, and not great at multitasking. They're cheap and come in big sizes. But we honestly wouldn't recommend using them anymore except for bulk storage or backups. For anything performance-based, games, apps, or your operating system, they're just too slow to keep up. In fact, some modern online gaming, like GTA roleplay mods, have issues running on hard drives because the disk can't load data fast enough. It's causing stutters, texture pop-ins, or even crashes. SSDs, on the other hand, have no moving parts. They use flash memory to store data, kind of like a giant USB stick on steroids. They're way faster, more durable, and boot up your system in seconds instead of minutes. Once you've used an SSD, going back to a hard drive feels like driving with the parking brake on. Most modern laptops and desktops now come with SSDs by default, but a lot of people still use a combination: SSD for the system and programs, and HDD for bulk storage like video files and game libraries. You can think of storage as your computer's closet. A hard drive is like a messy walk-in closet from 1998 with a light that only works half the time. An SSD is like a sleek modern dresser where everything is labeled and opens instantly. Now here's where people get confused. Your computer might have a ton of storage, but that doesn't mean it's fast. Storage is slow compared to RAM and the CPU. That's why when you launch a big program, it takes a few seconds. The computer has to go into the closet, grab the files, and copy them into RAM before the CPU can use them. Once they're in RAM, things move faster. But the speed at which they get from storage to RAM matters a lot. This is why faster SSDs like NVMe drives are so popular. They use a faster connection than older SATA drives. It's like switching from a country road to a freeway. For everyday users, the difference might not seem huge. But for big tasks like editing video or booting up 50 apps, it's night and day. And let's not forget about file organization. Your storage is only useful if you can actually find what you're looking for. Which is why you should probably stop saving everything to your desktop, like a digital raccoon. Yes, I'm talking to you. There are also external drives. These are storage devices you can plug in via USB or Thunderbolt. They're great for backups, transferring files, or pretending you're a spy while holding one. Speaking of backups, please make them. Storage devices can fail. Files get corrupted. Life happens. If it's important, back it up in more than one place. And no, the cloud doesn't count if you forget your password every 3 weeks. To sum up, storage is where your digital life lives. It's not fast, it's not fancy, but it's absolutely essential. And it's probably full of stuff you forgot you had, which is why it's called a closet of regret. If you've heard one thing about computers, it's probably this: it's all just ones and zeros. And yes, that's true. But also no, because that statement is way too simple to explain how this madness works. Let's break it down properly. Binary is the language of computers. It's a system made up of just 2 digits, 1 and 0. Why only 2? Because computers use electricity, and electricity is either flowing or not flowing, on or off, yes or no, it's true or false. It's a digital system with only 2 states. A 1 usually means electricity is flowing. A 0 means it's not. It's like flipping a billion tiny light switches super fast. Each switch is called a bit. A single bit can only store one of 2 values, 1 or 0. That doesn't sound useful, but combine a bunch of bits together and things get interesting. 8 bits make a byte. 1 byte can represent 256 different values. That's enough to store a single letter, like A or Z, or a sentence. That's hundreds of bytes. A photo, thousands, or millions of bytes. A video, now you're talking billions. That's where terms like kilobyte, megabyte, gigabyte, and terabyte come in.
Oh.
Each step up is about 1,000 times bigger than the last. And every bit of it, pun absolutely intended, is just combinations of 1 south and 0 south. Now, how does that actually turn into stuff? Let's say you want to store the number 5 in binary. It's written as 101, which literally just means plus plus equals 5. It's based on math, and computers are really good at it. But binary isn't just for numbers. We also use it to represent letters using systems like ASCII or Unicode. When you type the letter A, your keyboard sends a binary code like 01000001 to the computer. The computer reads it, and boom, you see an A on screen. Now imagine that happening millions of times per second. That's your computer, translating binary into text, images, sound, video, and memes. All of it behind the scenes is just strings of 1 south and 0 south being passed around like notes in class. What about images? Each pixel in a photo is just color data. The data is stored as numbers, binary numbers, telling your screen exactly how bright and what color to make each tiny square. So yes, even your selfies are just math. It's kind of romantic, right? Even music is binary. Yes. Every sound you hear from your speakers has been converted into digital data, stored as binary numbers representing sound waves. And when you hit play, the computer reads those binary codes and tells the speakers what to do. It's all incredibly precise, and yet completely invisible to us. We don't see the binary, we just see the result. But make no mistake, the computer is doing nothing but binary calculations, billions of times per second, and it never gets tired. Now here's where it gets mind-blowing. Logic gates. These are tiny electronic circuits inside your CPU that use binary to make decisions. There are gates called an OR, not NAND, nor an XOR. Each gate takes in one or two binary inputs and gives you a binary output. For example, an AND gate only gives a 1. If both inputs are 1, it's like asking, are both things true? If yes, then yes. If not, then no. These logic gates are the foundation of all computing. They're how your computer adds, subtracts, compares values, and controls everything. And they're built using transistors, those tiny switches we talked about earlier. Your CPU has billions of transistors. Billions. Each one flipping on and off, over and over, in carefully designed patterns. Those patterns are what run your operating system, apps, games, websites, everything. It's binary chaos, and it's beautiful. The thing is, humans don't write binary directly. We use programming languages. But even those languages get translated, eventually, into binary, so the computer can understand them. It's like speaking English, but your words get converted into beeps and blinks before they reach the listener. This translation layer is called compilation or interpretation, depending on the language. But in the end, it's all binary. Even your web browser has to be converted to binary before it can load your 10th tab about conspiracy theories. If you were to open a file in a raw text editor, you'd just see gibberish because you're looking at raw binary data. Without a decoder, it's nonsense. But with the right software, that binary becomes video games, spreadsheets, music, cat photos, and your uncle's badly formatted emails. So yes, computers are made of ones and zeros. But those ones and zeros aren't just numbers. They're switches. They're instructions. They're the smallest building blocks of everything you see on your screen. Binary is the foundation. It's the bedrock. The sacred language of the machine. May look dumb, but it's the smartest dumb system ever invented. And if you understand this, even a little, you're already ahead of 90% of people who use computers every day. Let's say you click on an app. You expect it to open, do what it's supposed to do, and not explode. But what actually happens when you click it? Short answer, your computer enters full goblin mode. Long answer, it activates a ridiculous layered system that makes modern software possible. Let's break it down in human terms. Every piece of software starts as code. Someone, somewhere, sat at a keyboard and typed out instructions in a programming language. Languages like Python, JavaScript, C++, or the one that made you cry in college, Java. But your computer doesn't speak Python, it speaks binary. So we need a translator. That's where compilers and interpreters come in. Some languages are compiled, meaning they get turned into machine code before the program runs. Others are interpreted, which means they get translated while the program is running. It's the difference between watching a dubbed movie versus one with live subtitles. But either way, the goal is the same. Turn human-friendly code into computer-friendly instructions. Once the program is translated, the CPU gets involved. It starts reading those instructions one by one, following them like a checklist. Draw a button, show a window, load the file. Play the sound. Each step is broken into a ridiculous number of smaller steps. Drawing a button might involve allocating memory, defining a shape, assigning a texture, calculating screen coordinates, and crying softly in the background. It all happens so fast, you don't even notice. Now, software doesn't work alone. It needs support from your operating system, the thing that manages files, memory, input devices, and 1,000 other boring but necessary jobs. So when software needs to open a file, it asks the OS for permission. When it wants to display something, it uses a library or a framework that talks to the screen. That's why installing software is sometimes complicated. It's not just the app, it's also the dependencies. Dependencies are other bits of code that your software needs to function. Think of them as coworkers. If they don't show up, the whole project falls apart. This is also why some apps break after updates, because one of their dependencies changed and now the app is confused, like showing up to your job and finding out your desk is gone. Modern software is made of thousands, sometimes millions, of lines of code. And they're written by humans, which means they're not perfect. Which means bugs happen. A bug is just a mistake in the code that causes something to go wrong. Could be minor, like a typo in a label. Or it could be catastrophic, like crashing your whole system if someone tries to name a file con. Yes, that actually happened. To help catch bugs, developers use tools like debuggers, testing frameworks, and late-night crying sessions. But no software is ever truly bug-free. They're just released when the bugs are small enough that most people won't notice. Another thing people don't realize is how software uses memory. When a program runs, it requests a chunk of RAM to work with. If it's poorly written, it might never give that memory back. That's called a memory leak, and it's the digital equivalent of leaving the tap running forever. Your system slowly runs out of usable RAM, and everything starts to crawl. Eventually, things crash or freeze, and you sit there, wondering why you thought running Chrome and Photoshop together was a good idea. Also, software often has to deal with hardware differences. One app might run on a dozen different kinds of machines, different processors, different graphics cards, different screen sizes. So the code has to be flexible, which makes it more complicated. That's why developers spend so much time testing software on different systems. They're not just being picky. They're trying to avoid emails that start with "your app broke my computer." On top of all that, software has to deal with user input, which means it has to prepare for everything. What if someone clicks the wrong thing? What if they type garbage into a form? What if they unplug the mouse while dragging a window? People are unpredictable. And so software has to be defensive. It has to assume we'll do weird things. And it has to handle them without falling apart. The best software is invisible. It just works, quietly and efficiently. The worst software makes you question your life choices. But behind every smooth app is a mountain of code, logic, error handling, and digital duct tape. So next time you open an app and it actually works, that's not luck. That's software sorcery at its finest. Let's talk about the most overhyped, overpriced, and misunderstood part of your computer, the graphics card, also known as the GPU, which stands for Graphics Processing Unit. And no, it's not just for playing games, although yes, that's what 90% of people use it for. The GPU's job is simple in theory. It draws stuff on your screen. But in practice, that job is absolutely insane. Every time you move your mouse, open a window, or watch a video, the GPU is calculating how to display it in real time. It has to figure out the position, color, brightness, shadows, and movement of every single pixel. And modern screens have millions of pixels, so it does this millions of times per second. The CPU could do this, technically, but it would be like asking a manager to deliver every piece of mail personally. It's just not efficient, so the GPU takes that load off the CPU's back and does it way faster. It's built for parallel processing, which means it can do thousands of tiny calculations at the same time. Perfect for graphics, which is basically just math wearing makeup. Now, there are two types of GPUs, integrated and dedicated. Integrated graphics are built into your CPU. They're fine for everyday stuff. Browsing the web, watching videos, editing Word docs, pretending to work. But if you want to play games, edit 4K video, or do 3D modeling, you need a dedicated graphics card. That's a separate piece of hardware with its own processor and its own memory, and its own price tag that makes your wallet cry. Seriously, GPUs are expensive, especially if you're chasing the latest and greatest models. Every time a new graphics card launches, gamers either celebrate or enter a mild financial crisis. And let's not forget the crypto mining craze, which pushed GPU prices into the stratosphere. For a while, buying a GPU was like trying to get concert tickets to a sold-out show in a time machine. Even now, some people hoard GPUs like they're gold bars. But what makes a good GPU? It depends on what you need it for. Gamers look at frame rates, how smoothly the card can render images in real time. Content creators care about rendering speed, color, accuracy, and hardware acceleration. And some people just want a GPU that won't catch fire under load. Modern GPUs also handle more than just visuals. They're used in AI, scientific computing, video editing, machine learning, and cryptocurrency mining. Because they're so good at fast, repetitive calculations, they're ideal for tasks that would crush a normal CPU. In fact, your browser and even some websites use GPU acceleration behind the scenes to keep things smooth. Now let's talk about VROM. That's the memory on your graphics card. And it's different from system ROM. VROM holds textures, shaders, and frame data needed to render complex scenes. More VRAM means the GPU can load more visual detail at once, like higher resolution textures in games. But just like regular RAM, having more doesn't always mean better performance. It has to be used efficiently, and some games just don't need much. That said, try running a modern game at ultra settings on a 2 GB GPU, and you'll hear your computer scream. Also, keep in mind, your monitor matters too. If you're using a 4000 display or a high refresh rate monitor, your GPU has to work harder. Pushing more pixels at higher speeds takes more horsepower. And don't forget about cooling. High-end GPUs generate a ton of heat, and if they overheat, they throttle performance or shut down. That's why they have fans. Big ones. Loud ones. Sometimes it sounds like a jet engine is inside your case, which is great if you like realism in your flight sims. So yeah, graphics cards are powerful, complicated, and stupidly expensive. But if you're into gaming, design, video editing, or flexing on forums, they're a must. Just be prepared to sell a kidney. Or two, if you want RGB lighting. Let's talk about the referee everyone forgets. The operating system, or OS, is the quiet babysitter inside your machine. Windows, Mac OS, Linux, Android, and iOS are different faces of the same job. Its primary mission is to keep hardware and software from fighting each other. Think of the OS as a hotel manager. Guests are applications. Rooms are hardware resources. The manager assigns keys, schedules cleaning, and stops guests from stealing towels. Without an OS, every program would try to grab the entire building. The OS starts working the moment you power on the computer. First, it checks the hardware to make sure nothing is on fire. Then it loads its own core into RAM. That core is called the kernel. Kernel is the boss of all bosses. It has absolute control over memory, CPU time, and input-output. When an app needs something, it asks the kernel politely. If the request is safe, the kernel says sure and opens the door. If the request is weird, the kernel slams the door in its face. This is called protection. It stops one broken program from sinking the entire ship. Your desktop or home screen is not the kernel. It is a fancy jacket called the user interface. The interface translates clicks and taps into polite kernel requests. That is why moving icons feels instant, while deep tasks take longer. The OS also handles files, decides how data is stored, named, and retrieved. Deleting a file does not erase it immediately. The OS just forgets where it is, like misplacing a TV remote. Eventually, new data overwrites the spot. That is why recovery software sometimes resurrects embarrassing photos. Drivers are another OS job. A driver is like a translator between hardware and the kernel. Got a new printer? Without the right driver, the OS just shrugs. Updates are the OS version of vitamins. They patch bugs, close security holes, and occasionally break everything. That is why people fear the phrase restarting to finish updates. Multitasking is also under the OS umbrella. It slices CPU time into tiny chunks and hands them out. To you, it looks like apps run simultaneously. In reality, they take rapid turns faster than you can blink. Memory management is similar. The OS hands out slices of RAM and reclaims them when apps close. A memory leak is when an app refuses to give its slice back. The OS can swap inactive data to the storage drive to stay afloat. That process is called paging, and it hurts performance. Virtual machines are another trick. The OS can pretend to be hardware and host a second OS inside itself. It is computing inception, useful for testing or running legacy software. OS choice sparks endless internet wars. Windows has games, Mac OS has design cred, Linux has command line, street pride. Underneath the logos, they all still babysit hardware and schedule tasks. Mobile systems do the same job with touchscreens and battery rules. No matter which flag you fly, The OS is the glue that keeps the experience human-friendly. Treat it well, install updates, and maybe thank it once in a while. Because without that babysitter, your computer would be a toddler with a soldering iron. Let's zoom in on a moment that happens 100 times a day. You press a key on your keyboard. A letter pops up on screen. It feels instant. But behind the scenes, an entire chain reaction just went off. Let's walk through it. You press the letter A. Your finger physically moves a keycap downward. Underneath the key is a switch, usually a membrane or mechanical contact. That press completes an electrical circuit. Your keyboard's internal chip detects the signal and translates it into a key code. That key code is a number. Each key has a unique one. For A, it might be 65, depending on the encoding system.
Oh.
This signal travels from the keyboard to the computer via USB or Bluetooth. The operating system catches the signal. It sends it up the input handling system. The OS decodes the key code and checks what should happen. Are you typing in a text box? A search bar? A cheat code field? If yes, the OS sends the signal to the active program. The program's code says, "Oh, a key press." It receives the key code, processes it, and updates its visual display. The letter A now appears in your text editor or browser. But it's not the actual letter yet. It's a string of binary data telling the screen which pixel pattern to light up. The GPU helps by rendering the shape of the letter on screen. Fonts come into play here. The software asks the system font engine how A should look in that size and style. Then it draws the shape, fills it with color, and places it at the cursor location. All of this happens in milliseconds, faster than you can blink. And if you hold the key down, a repeat signal starts firing at set intervals. That's how long strings of letters appear when you lean on the keyboard. Now multiply this process by every key you press, every mouse click, every gesture. Each one is a small electrical event turned into digital meaning. It feels natural, but it's not. It's highly engineered. People spent decades refining keyboard layouts, input response times, and character encoding standards. Even emoji have Unicode codes, so when you type a smiley face, you're really sending a fancy binary value. Different systems interpret those codes in different ways. That's why the emoji you sent on your Android looks weird on your friend's iPhone. Keyboards themselves also vary. Mechanical ones use physical switches. Membrane ones use pressure pads. Gaming keyboards might have lighting, macros, or onboard memory, but all of them boil down to this: press, detect, code, process, render, display. That's what happens when you press a single key. It's not magic. It's an electric dance choreographed at the speed of light. You're online right now. Watching this means your device is part of the internet. But what even is the internet? It's not a cloud, it's not magic, it's definitely not wireless fairy dust. The internet is a massive physical network. It's made of cables, routers, switches, satellites, and servers. Real stuff, tangible stuff. Miles and miles of it. At its core, the internet is just a giant system for moving data from one machine to another. That's it. Your device connects to a local network, usually through Wi-Fi or an Ethernet cable. That local network connects to a router. Router talks to your modem. Modem connects to your internet service provider, your ISP. That ISP is like your internet travel agent. It finds the best path for your data to reach where it's going, and your data has a lot of places to go. Every website you visit lives on a server somewhere in the world, not the cloud. An actual building filled with computers. These buildings are called data centers, and they're huge, loud, cold, and kind of terrifying. When you type in a web address, something magical happens. But not really magical, just technical. Your device contacts a DNS server. DNS stands for Domain Name System. It's like the internet's phone book. You ask for google.com, and DNS gives you an IP address. That IP address is the exact digital location of the server you want. Then your request travels across networks, jumping from router to router, crossing countries, even underwater. Yes, the internet has literal underwater cables, thousands of them, stretching across oceans. Data travels through fiber optic cables at near light speed. And that data is split into tiny chunks called packets. Each packet carries a piece of the full message, plus instructions on how to reassemble it. Think of it like mailing 1,000 puzzle pieces in separate envelopes. They don't all take the same route, but they all arrive eventually. When they reach the destination server, it reassembles them and sends back a response. Same process in reverse. All of this happens in milliseconds. That's why clicking a video loads so fast, unless your connection is garbage. The internet is also decentralized. No single person owns it. No single server controls it. It's a collaboration of networks, ISPs, corporations, and governments. That's what makes it powerful, and sometimes messy. There are protocols to keep it organized. TCP/IP is the foundation, rules for how packets are sent and received. HTTP and HTTPS handle websites. FTP is for file transfers. There are hundreds of these little rulebooks working behind the scenes. Security is a big deal too. That little padlock in your browser? It means your data is encrypted. Only the website and your browser can read what's being sent. Without encryption, everything would be exposed. Your passwords, messages, photos, all visible to anyone snooping on the line. That's why public Wi-Fi can be risky. Unless you're using a VPN. And yes, we'll talk about VPNs later. Streaming, gaming, messaging, social media, it's all just data being sent and received at incredible speeds. So the next time your video buffers, don't blame your computer. Blame the massive, fragile, brilliant infrastructure behind the scenes. Because the internet is not just a series of tubes. It's a miracle of engineering held together by duct tape, global cooperation, and a suspicious amount of cat videos. Let's take a minute to talk about something that's always running in the background: security. Because while computers are powerful, they're also a massive target. Every time you go online, you're stepping into a digital jungle. Hackers, viruses, data leaks, pop-ups that promise you a free iPhone. It's chaos. But your system isn't completely defenseless. In fact, it has several layers of protection working quietly behind the scenes. Let's start with the firewall. No, it's not a wall made of fire. It's a piece of software or hardware that controls what comes in and goes out of your network. Think of it like airport security. It checks incoming and outgoing traffic, and it blocks anything suspicious. Most operating systems have a built-in firewall. Windows, Mac OS, and even your router have them. They're usually turned on by default. Which is good because you probably forgot they existed. Next up, encryption. This is the reason you can shop online without giving your credit card number to every creep on the internet. Encryption scrambles your data so that only the intended recipient can read it. It's like turning your message into a secret code. And even if someone intercepts it, they can't understand it without the key. Modern websites use HTTPS. That little padlock in the browser, that's encryption in action. It means the connection between your browser and the website is secure. Everything you send is encrypted before it leaves your device, decrypted when it arrives. The same idea applies to messaging apps. Services like WhatsApp and Signal use end-to-end encryption. So only you and the person you're chatting with can see the messages. Not even the company running the app can read them. Encryption is everywhere now. Your files, your passwords, your banking apps. It's the reason you can trust your phone not to spill your secrets. Most of the time. Which brings us to passwords. It's the most basic and most abused form of security on Earth. If your password is password, we need to talk. Same goes for 123,456, or anything with your dog's name and a birth year. Passwords work best when they're long, random, and unique, but that makes them hard to remember, which is why password managers exist. They store all your complex logins behind one very strong master password. If you don't use one, you're probably reusing passwords across sites, which is a hacker's dream. Because if one site gets breached, they try that same password everywhere else. It's called credential stuffing, and it works way too often. Also, two-factor authentication. Use it. Always. It adds an extra step, like a text code or app notification, on top of your password. So even if someone steals your password, they still can't get in. It's like locking your door and then putting a bouncer behind it. Your system also protects itself from malware. That's software designed to mess things up. Viruses, worms, ransomware, spyware. Operating systems now have built-in tools to detect and block this junk. and web browsers have blacklists for dangerous sites. If you're about to click something sketchy, they'll often warn you first. But even with all this protection, user error is still the weakest link. Most hacks don't happen because of genius-level coding. They happen because someone clicked the wrong link, or opened the wrong file, or typed their password into a fake website that looked just real enough. This is called phishing. It's when someone pretends to be legit to steal your info. Fake emails, fake websites, fake login screens. It's not high tech, it's just good acting, so stay suspicious. If something looks off, it probably is. And if someone tells you your account will be deleted unless you log in immediately, take a breath, then delete it, because your system can do a lot. But it still counts on you to be the first line of defense. Everyone talks about the cloud like it's some mystical, invisible force. But here's the truth. The cloud is just someone else's computer. That's it. That's the punchline. When you save something to the cloud, you're uploading it to a server in a data center somewhere. It might be in your country. It might be across the ocean. You don't know, you don't care, and that's the point. The cloud is just a fancy term for remote storage and services. Instead of running software or saving files on your own device, you're using someone else's hardware through the internet. Cloud storage is the most common example. Google Drive, iCloud, 1A Drive, Dropbox, these are all cloud-based file cabinets. You upload your documents, and they live on servers owned by tech giants. When you open a file, it's streamed to your device. When you edit it, the changes are synced back to the server. This is why your stuff appears the same on all your devices, because none of it lives entirely on your device anymore. Then there's cloud computing. This is when software, processing power, or entire applications run on cloud servers instead of your own machine. Think of it like renting a supercomputer by the minute. Platforms like Google Cloud, AWS, and Microsoft Azure offer this to companies. It's flexible, scalable, and insanely powerful. Streaming games from the cloud. Same idea. You're not playing on your console or PC. You're controlling a machine in a warehouse somewhere via the internet. Your input goes up. The video stream comes back down. If the connection's bad, it lags. If it's good, it feels seamless. But again, it's all just computers, just not yours. The cloud also powers backup services. Instead of saving files on a USB stick, you back them up to the cloud. This way, even if your device explodes, your data is safe, assuming you remember your password. Cloud apps like Google Docs, Canva, or Notion don't need installing. You use them through your browser. The code runs on remote servers, and your device just acts like a window. This also means updates happen automatically. You always get the latest version. No downloads, no patches. Businesses love the cloud for the same reasons. They don't need huge IT departments anymore. You can rent storage, software, and processing power on demand. It's cheaper than running your own data center. But it's not perfect. Cloud outages happen. When they do, entire companies go dark. No emails, no logins, no files. Because everything relied on someone else's infrastructure. Privacy is another concern. Your files, messages, and data are sitting on someone else's machine. Sure, they're encrypted, but they still exist somewhere. And if that company gets hacked, your stuff is at risk. So while the cloud is convenient, don't treat it like a vault. Treat it like a very polite stranger holding your stuff behind a velvet rope. Useful? Yes. But keep a backup, just in case that stranger changes careers. The cloud isn't the sky. It's a server rack in a warehouse with blinking lights and bad ventilation. And thanks to that warehouse, your life runs smoother until it doesn't. There are a lot of tech myths floating around. Some are old, some are weird, some just refuse to die. So let's bust a few, starting with the classic. Leaving your laptop plugged in will ruin the battery. False, modern. Laptops have smart charging systems. Once the battery hits 100%, charging slows down or stops entirely. Leaving it plugged in won't destroy it. What hurts batteries more is heat. So if your laptop runs hot, unplugging now and then can help. Next up, more signal bars means faster internet. Also false. Signal strength and internet speed aren't the same thing. You can have full bars and still get slow speeds if your network is congested. It's like having 5 open lanes on a highway. It's all stuck in traffic. Another myth. You need to safely remove USB drives every time. Technically. Sometimes. Modern systems use something called write catching, but it's often disabled for small devices. Still, to be safe, yeah, hit eject if you're paranoid. Next myth. Macs don't get viruses. Completely false. They do. They always have. They just get fewer viruses than Windows machines because fewer people target them. It's not immunity, it's popularity. Another one. Incognito mode makes you anonymous. Big nope. Incognito only hides your history from the device you're using. Your ISP employer or the website you're visiting can still see what you're doing. Next, more megapixels means a better camera. Nope. Megapixels only measure resolution, not quality. Lens quality, sensor size, and image processing matter way more. This is why a 12MP DSLR looks better than a 48MP budget phone. Out this one. Closing background apps makes your phone faster. Not really. Most phones handle background apps efficiently. Forcing them closed can actually make your phone work harder when reopening them. So unless an app is frozen, let the system manage it. Another myth. Overnight charging kills your phone battery. Modern phones are smart. They stop charging at 100% and even slow down charging during sleep hours. The real killer is using sketchy chargers or overheating. Next, HDMI cables affect picture quality. Wrong again. HDMI is digital. Either the signal gets there or it doesn't. Expensive cables won't give you a cleaner image unless you're going 50 feet or more. Cheap cables are fine. Here's a juicy one. Airplane mode saves your battery. It's true, but not magic. Airplane mode turns off wireless radios, which can reduce power usage. But if you're playing games or watching videos, your screen is still the biggest drain. Another one. Antivirus software is useless now. False. It's less essential than it used to be, especially if you're careful. But good antivirus can still help catch phishing, malware, and unsafe downloads. Last one. The more RAM you have, the faster your computer. Sort of, if you're running out of RAM, then yes, adding more helps. But if you already have enough, adding more does nothing. It's like adding more seats to a bus with only 5 passengers. So why do these myths persist? Because tech is confusing. Because people repeat what they hear. And because companies sometimes let bad info slide, if it helps them sell things. So the next time someone drops a tech fact, check it. Not every tip is true. And not every expert knows what they're talking about. Especially that one guy in your office who always brings up Linux. Let's talk about upgrades. Specifically, how most of them are overhyped, misunderstood, or completely unnecessary. Because in tech, throwing money at a problem doesn't always fix it. First off, know your bottleneck. A bottleneck is the part of your system that's slowing everything else down. It's not always what you think. Your games aren't lagging because your GPU isn't good enough. Sometimes it's your CPU, or your RAM, or your slow old hard drive. If your GPU is powerful, but your CPU can't keep up, it creates a bottleneck. It's like having a supercar stuck behind a tractor. No matter how fast the back of the system is, the front is holding it up. So before you upgrade anything, figure out where the real problem is. Do your fans sound like they're about to take off? Might be thermal throttling. Do apps open slowly? Might be your storage. Does your system crawl with multiple tabs open? RAM. Does it lag in games but run fast in everything else? Could be your graphics card. Too many people drop hundreds on one component without fixing the actual issue. Worse, they upgrade everything just to say they did. Which brings us to the second point. Don't chase benchmarks. Yes, they're fun. Yes, seeing big numbers on a chart is exciting. But if your daily work is browsing, emails, and light editing, you don't need the latest hardware. A used laptop from 5 years ago could be more than enough. Upgrades are only upgrades if they solve a real problem, not just if they make a Reddit comment section jealous. That said, some upgrades do make a big difference. Switching from a hard drive to an SSD, huge doubling RAM from 4 GB to 8 or 16 GB noticeable. Moving to a better display with higher refresh rate, smooth as butter. But going from 32 GB of RAM to 64 GB for watching YouTube, that's just flexing. Another trap, buying ahead. People buy hardware for tasks they'll maybe do someday. I'm getting this GPU so I can edit 4K video once I start my YouTube channel, which I haven't started yet. If you don't need the power today, Don't spend the money today. Tech gets cheaper. New stuff keeps coming. Buy what solves your problem now, not what might impress someone later. Also, be wary of brand hype. A flashy logo doesn't always mean better performance. Same with RGB lights. They make your PC look like a nightclub, but they won't make your Excel sheet any faster. When in doubt, upgrade for stability, speed, and comfort, not for bragging rights. Spend money where it matters. Your monitor, your keyboard, your chair. Because let's be honest, you'll notice a bad chair way before you notice a 2% bump in frame rate. The real power move. Knowing when not to upgrade. When you resist the urge to spend on hype and invest in what actually improves your experience. And sometimes, that upgrade is just cleaning the dust out of your case. Let's talk about the thing that's taking over headlines, classrooms, and probably your search history. Artificial intelligence, or, as it's often sold, the future. But what is AI really? At its core, AI is just software that can make decisions based on data. It's not magic, it's not self-aware, and it's not coming for your job tomorrow, probably. Today's AI is narrow. That means it's good at one thing at a time. It's like recognizing faces, or predicting text, or recommending videos you regret watching. These systems are trained using data, tons of it. Images, words, sounds, code. The AI looks at all that and learns patterns. Then, when you give it new input, it uses those patterns to guess what should come next. That's all it is. Glorified guessing. But it's getting scarily good at guessing. AI tools can write, draw, code, translate, and even hold conversations. Some of them sound almost human. Others sound like a robot with a drinking problem. But none of them understand what they're doing. There's no thinking, no awareness, just prediction. Give it a prompt, it gives you a response based on statistical probability. It's impressive. It's useful. But it's not alive. Still, that doesn't mean it's harmless. AI raises huge ethical questions. Who owns the data it was trained on? Can it replace workers? Should it? What happens when people trust AI too much? When it spits out wrong information with total confidence? Bias is another problem. AI systems can absorb the same biases found in their training data. If the data is flawed, the AI is flawed. And often, the people using it don't even realize. Then, there's the issue of automation. AI can already write code, diagnose diseases, generate music, even produce legal documents. That's great if it helps people, not so great if it replaces people. But AI also has incredible potential. It can speed up research, help diagnose illness faster, translate languages in real time, find patterns no human could spot. The key is how we use it and who gets to use it. Because right now, most powerful AI models are owned by massive corporations. They decide how it's trained, what it's used for, and who gets access. That's a lot of power in a very small number of hands. So yeah, AI is exciting, but it needs oversight, transparency, and probably a giant "do not trust blindly" sticker. What about the future? Eventually, AI might become more general, able to learn any task, not just one. That's called AGI, Artificial General Intelligence. It doesn't exist yet, but people are racing to build it. Some say it'll revolutionize everything. Others say it'll doom us all. The truth is probably somewhere in between. I will change computing forever, just like electricity, the internet, and smartphones did. But it won't make computers think like us. Because right now, and for the foreseeable future, computers are still just machines. Incredibly fast, incredibly smart machines. But still machines, and AI, it's just the next layer on top. Use it wisely, use it carefully. And maybe, just maybe, don't ask it to write your wedding vows. So, here we are. Almost an hour later, you've made it through the inner guts of the modern computer. The hardware, the software, the myths, the mess, and the magic. You now know more about how computers work than most people who use them every day. That's not a dig, it's just how invisible all this stuff is. We rely on technology constantly, but we rarely ask what's actually going on under the hood. And when you do ask, the answers are weird. The CPU isn't a brain, RAM isn't memory, the cloud isn't in the sky, and binary, still just a bunch of 1 south and 0 south doing the heavy lifting. Computers are dumb, but they're fast. And they only do what we tell them to. which means if you understand the rules even a little, you can make them do a lot more. You can troubleshoot smarter. You can upgrade with purpose. You can explain things to friends and family without sounding like a wizard. And best of all, you can stop falling for tech myths that belong in the digital stone age. No, expensive HDMI cables aren't worth it. Yes, Chrome is eating your RAM again. No, that guy in your office doesn't actually build computers for fun if he still thinks RAM is storage. You've got the knowledge now. You've got the power. And hopefully, a newfound appreciation for the ridiculous complexity of the machines we use every day. Now go forth, plug things in, and plug them when they stop working. And remember, it's not magic. It's just very, very fast math. So, thanks for watching, and I will see you later.